Hi, everyone. Welcome to the 6th Clever Planet seminar. My name is Damanveer Gariwal, and I'm from Rice University. So before introducing you to today's speaker, I'll have a brief introduction about the Clever Planets group. So Clever Planets is a multi-institutional interdisciplinary initiative to unravel the conditions of planetary habitability in our solar system and beyond. Its lead institution is Rice University and is supported by NASA. It's one of the teams of the Nexus for Exoplanetary Science System Coordination Network under astrobiology. Before we start, I'll also have a brief land acknowledgement statement. Our research at Rice University is pursued on the traditional territory of several native peoples, namely the Karankawas and the Sanas, as well as the Kohikutans, represented today by the Tapilam Kohikutan Nation, and the Aishaks, represented today by the Atakapa Ishak Nation. We see as a duty to acknowledge this historical aspect of our identity and to foster a beneficial environment for all communities, in particular those who preceded us on this land. So it's my great pleasure to introduce you to today's speaker, Caroline Dorn. She studied geophysics. She studied her geophysics at Leipzig and ETH, followed by a PhD in Luzon in hydrogeophysics and environmental science. After that, she did a postdoc in exoplanetary science in Bern until 2017, and presently she is an Ambizione fellow at University of Zurich. So, Caroline, the stage is all yours.
Thanks so much for the introduction and welcome everybody. So let me just arrange some windows. Okay. Yeah, welcome everybody. So today I want to share you some new insights into planetary interiors. There are mainly two topics that I will speak about, but I will lead you through this seminar. Okay, to start with, I want to introduce my talk with showing you data on well-characterized exoplanets. Here you see a mass radius plot where you have some Super-Mercuries down here, some super-Earths and sub-Neptunes. So this is mainly the planet populations, the planet population of interest to me. I like to show this data in a different way, namely by showing you also again planetary mass, but on this x-axis here I show you the normalized density of these planets, where you nicely see the high density planets, the Super-Mercuries, well separated from the super-Earth population, and the very low density planets on the left. So the main question is, what are these planets made of? What are their interiors made of? Because their interiors will, to know what their interiors are made of is a direct link to better understand their formation and evolution processes. And traditionally, we would explain these high density Super-Mercuries with very large core sizes. And as we go to the left of an Earth-like density or interior, we have planets that we normally explain with lots of volatiles, water or gas. So at first sight, it seems very simple, the picture of interior diversity that we have on this plot. So from the right of an Earth-like interior, we have larger cores, whereas on the left of an Earth-like interior, we have more water and gas on top. But in recent years, we learned that the complexity of these worlds is much more complex much more complex than the simple picture suggests. And the reason is that these planets are hot worlds. So these simple pictures or these simple interiors where we have cold, rocky interiors, for example, this may not apply to the majority of planets in here. And to illustrate this, I've just plotted in reds all those planets where that lie within the greenhouse limit. So any atmosphere on top will rise their temperatures high enough such that the interiors must be molten. There are magma oceans underneath. And in addition, these planets in orange, they have very high equilibrium temperatures such that even if they are bare rocky worlds, they are hot enough to have magma oceans. There are only few exceptions. You see the TRAPPIST-1 planets down here, and there's LHS 1140b hidden in here. And so in this talk, I will focus on two things, two aspects. One, the first question is, what is the diversity of rocky composition? So is there a diversity, or can we understand this scatter in super Earth densities by simply variability in rock compositions? And the second is, and the second topic is about magma oceans, these magma oceans that should be very common among super Earths as well as sub-Neptunes, and how these magma oceans can actually store also a lot of volatiles. So I will first talk about the rocky interior diversity. And let me discuss this diversity of rocky interiors by, I'm sorry, my daughter is screaming in the back. I hope it doesn't disturb you as much as it does to me. So the rocks that build the planets, these rocks, they are formed in protoplanetary disks, and they condense out in these disks at generally very high temperatures. So wherever building blocks form in these protoplanetary disks, they would generally inherit the abundances of rock compositions, like these rocky species, for example, from the disk. And a good proxy for this is the abundance of these elements that we can measure in the stellar photosphere. And this link between planets and stellar composition has been explored by various studies in the past, and I just and I will lead you through a short history of what happened in that field. So let's have a look first how good the assumption is that the relative refractory abundances of a planet are simply or can be informed by the stellar proxy. And I want to look at the Earth case. So here in yellow, you see the normalized stellar or solar abundance, and in blue, the estimated abundance of various elements from the Earth. And so you see that iron and silicon and magnesium that form most of the rocks, they are slightly depleted, but the depletion is maybe similar among these elements. So in short, the solar proxy does mirror the Earth's abundances to within 10 mole percentages. However, the effect on the density due to this depletion is negligible. So the stellar proxy seems for the Earth to work to first order. But what about the abundances of other stars? So here you see the overall stellar variability of rock-forming elements with the Earth and the Sun highlighted in here. When you translate this variability to a mass radius plot, that's the red region that we see in here. And in this work, Plotnikov and Valencia show that the variability of these element ratios in planets is larger than in stars, as the spreads of planets that extend further than this red region is giving the evidence for this. So these lower density planets, they could be explained by having more volatiles and still agree with the stellar proxy. But these planets down here of high densities, they simply cannot be explained by the overall distribution of stellar abundances. And in a recent study of Adi Bekian, we demonstrated on a sample of 22 planets that there is actually a correlation between the stellar abundances and planet composition. So here I show you the stellar abundance on the x-axis and planet density on the y-axis. And there seem to be two populations, like some super-Mercuries and super-Earths, but there seems to be a clear correlation in between. So this gives evidence that there is a link between or that the planets inherit the chemical signature of what we can measure in their stars. And very recently we added, or Vardan added 6 other planets to this, and they actually match pretty much the trend. This planet, for example, there are some databases where this planet doesn't appear because it's not as well characterized. So it seems actually very nice that this trend might actually be true. Okay, maybe I will skip these other aspects, but yeah, I want to also show you this correlation in this parameter space. So iron over the combined magnesium and silicon weight of a planet versus its stellar components. There is this clear correlation again, and in addition, we see a very distinct population, or the population of super-Mercuries seems very distinct in this parameter space. If giant impacts would be the formation process that forms these super-Mercuries, we would actually expect a population of planets that is smoothly connecting super-Earths to super-Mercuries. Here, it seems not to be the case, although I must say the data is sparse and errors are large. So at this point, we can't say more about this, but yeah, it's interesting that these populations seem to be quite disconnected. An alternative mechanisms exist, additional to impacts that have been looked at, and here I simply list some references where giant impacts are not needed to form iron-enriched bodies. There is another aspect in the inheritance of refractory elements of planets. So even if the refractory element budgets of a planet are simply inherited by the star or with a certain ratio, there can still be quite some differences in the final bulk composition of a planet, and this is due to different oxygen contents. So meaning that the iron that a planet inherits can either be oxidized or and in the mantle, or metallic and in the core. And the effect of this is what I'm plotting in here. So in red, you would see the diversity of planetary mass radius if they simply inherit the stellar ratio, and where all the iron is in the core, and in green, this is the range where all the iron is oxidized in the mantle. And there are good arguments for from Doyle et al. Why oxidation states are maybe not as extreme as these two end members that I'm showing you here, but that they are rather similar to objects in the solar system. Nevertheless, in line with Doyle et al., we showed in another publication of the TRAPPIST-1 system that there's a possibility for the TRAPPIST-1 planets to be very rich in oxygen. So if we simply assume the refractory ratios to match a solar composition, then it turns out that all 7 planets are consistent with a core-free and fully oxidized composition. This is just one of more explanations, but it's a curiosity, I would say, that there is one interior solution that matches them all. Okay, I will come now to the second topic. So I talked about like what leads to this diversity in bulk densities in the overall distribution of super-Earths. And I talked now about the rock diversity, but what about volatiles, and where are volatiles actually stored? And I will show you in this part how simple models may not be appropriate to explain the diversity of super-Earths or sub-Neptunes, and that we have to look at new models. And so far, actually, formation and evolution studies, they use rather simplified interior models, simplified in the sense that they are assuming a cold, rocky interior as depicted in here with the gray core and the black mantle, and that they are separate from any volatile layers of water or gas. And these simple models have been used, for example, to interpret this bimodal distribution. This is among the most important constraints that we have to interpret super-Earths and mini-Neptune interiors. And I guess you all know this bimodal distribution has been explained by evolution models, for example, evaporative loss or core-powered mass loss. And both these theories, although they work on different timescales and a bit different, anyway, they both predict that mini-Neptunes, they must have retained hydrogen-helium envelopes, while the super-Earths are the stripped cores of these mini-Neptunes. And there are also some studies, not just Owen and Wu, also there's a Jin and Modesini paper on this, that predicts that these stripped cores, the super-Earths, must be dry worlds without any water in order to match this bimodal radius distribution. There are other alternative explanations to this bimodal structure. We have Moses et al. Who argue that this bimodality can be also explained by sub-Neptunes being simply rich in water, but there are limitations to this explanation. And we have a formation evolution study from Venturini et al., where she and co-authors showed that simply having planets forming within and outside the water ice line creates naturally a bimodal distribution, while these sub-Neptunes can also have hydrogen-helium envelopes on top of a water layer. Okay, so these simple models that were employed in all these studies, they have limitations, and the limitations are, yeah, I will explain them in the next slide, because they are neglecting magma oceans. However, magma oceans must be common. As I said in the beginning, super-Earths and sub-Neptunes, they are warm and hot worlds. They allow for magma oceans to be present for the majority of planets. Second, water should also be a common component, as water, if it's not accreted during formation, can be endogenically produced simply by the reaction of a primordial hydrogen envelope with an oxidized magma ocean underneath. And if you have a magma ocean with volatiles in contact, then by necessity, these volatiles, for example, water, they will partition into the magma ocean, as magma oceans represent huge sinks for volatiles. And yeah, maybe the question is why don't we yet have comprehensive interior models that we've used to interpret observed exoplanets that account for all these aspects? And I think the reason is the following. So traditionally we have studies on ocean worlds that neglects any interaction between water and the rock underneath. They care about the different phases of water, and so they have a different focus. Then we have these magma ocean worlds. They traditionally come from the geoscience community. They are looking at small water mass fractions or small volatile fractions as we know them from Earth, and they study how these volatiles outgas and how these planets cool. So they are not using large amounts of water, and thus they are also not considering density effects due to these the water in the interior, like in general. There are, of course, some studies that looked into other aspects as well. I just want to highlight here the study by Alona Vezan on water that is mixed in the melts for sub-Neptunes. And I'm sorry. And here I want to show you for the first time the effects of water that is stored in magma oceans on the actual radius that we can probe. So yeah, I will tell you what the effect is on the total radius due to this effects by water being mixed with the magma. And I will show you this, or I will demonstrate you this on a series of mass radius diagrams that I will walk you through in the next slides. So here on this mass radius diagram, I show you a Earth-like cold rocky interior, so no magma ocean. If I add now a steam atmosphere on top of 5.4%, then the radius increases drastically as expected. But now this interior model is actually unphysical, as the surface temperatures are so high underneath the steam atmosphere that the rock must be molten. So if I allow the rocks to be molten, I get an increase in the total radius again, as I have a phase change from solid to liquid rock. But again, this model is unphysical, as water and magma by necessity should mix. And if I allow for this mixing, then I get much smaller radii. Okay, and if I also use a smaller percentage of water for these mass radius curves, then I get the same picture, but these lines are just more closely packed. So in the study, we have compared these three interior models. So the black one is one that is very commonly used, where we have a cold, solid, rocky interior. And this red model is more advanced, as it accounts for magma oceans, but and it yields the largest radii in general. And when we allow actually for water to dissolve into the magma, then we get the smallest radii in general. And the reason for this is the following. On the atomic scale, you can imagine if you have water in the magma, water is a relatively small molecule compared to molecules of silicate melts. And so the increase in volume of magma with water is simply limited compared to magma that is dry. Yes. So let's do a more quantitative comparison between these models. Here I show you the difference between the magma ocean that is separated from a steam atmosphere, and here is the model with the water that is dissolved in the magma ocean. And here is the relative differences, or here I plot the relative differences between these models. They, as you see, sorry, these differences are first of all large, up to 16%. So they are comparable to observational uncertainties, and they are a function of the water mass fraction and a function of planetary mass. Here I show you our new generation model with compared to the most commonly used model. And the differences in that case are a factor of 2 smaller, but the trends with planet mass and water mass fraction are very similar. Now I want to discuss what is actually the effect on the inferred water mass budget. So if you have observed mass and radius data for an exoplanet, how different can your water mass budget's estimates be, depending on the interior model that you're using? And here, for a very small mass body of 0.3 Earth masses, I show you that the inferred water mass fraction on the y-axis can be an order of magnitude different depending on the interior model that is used. And for larger masses, so here I go to larger masses, the effect is smaller, and the effect is smaller as for larger bodies, the pressure gradient in the interior is steeper. So the extent of a magma ocean is much more limited for larger mass bodies if all these planets have the same boundary conditions. So let's have a look at some previous exoplanet cases. So we have for example, the relatively cool TRAPPIST-1 planets, and especially the inner planets are of interest in here. So even though the inner planets are within the runaway greenhouse limits, their atmospheres must be very thin, and they are too thin to raise the temperatures in their interiors high enough in order for the surface rocks to be significantly molten and to store enough water within them. So what I find is that the dissolved water in the interior of the TRAPPIST-1 planets is marginal. Let's have a look at this Loopy B planets that was recently announced by Leticia Del Rez and co-authors. In their study, their water estimates are very large, about 12 weight percentage of water for this actually very hot planets, which is due to their imposed assumption of water being condensed. We find that if we take our interior model, we find a steam atmosphere could be present of about 0.07 weight percentage, and there could be much more water stored actually in the magma ocean underneath, up to 2 weight percentage. We haven't done a full inference analysis, that would provide more details into this, but yeah, this is future work. And let's have a look at this very high, this very hot world's 55 Cancri E. This planet is so hot that it's believed to have definitely a molten interior, but maybe with a mineral-rich atmosphere, and water is not among the strong candidates of compositions to be present on its surface. And for this planet, still we find that several percentage of water could be stored in the interior, while very little could be present on as surface water. I think for the future, for this planet, an evaporation model that would actually take into account the effect that water could be stored in the magma and be released as water is eroded from the planets. That would be very interesting to look at and to investigate whether this planet could still harbor some amounts of water or must be dry. So overall, these previous interior interpretations, they have looked at surface water reservoirs only, but our study shows that the amount of water that is stored in the deeper interior can exceed the water budget that can be present on the surface. So I come to the conclusion. So first of all, water, I think, is a very common component in the interiors of sub-Neptunes and super-Earths. Magma oceans are very, very common, as these planets are hot, warm or hot worlds. We actually have very few exceptions of temperate planets so far. And if you have a magma ocean, these magma oceans represent huge volatile reservoirs. And I've shown you this for water. In this case, that's simply the water that can be stored in these interiors can be significant. And I think we need to reinvestigate previous interpretations of the bimodal distribution, for example, as well as individual interior characterizations of targets. And there are also some implications from this magma ocean study. And this is, for example, that the estimates of evaporative loss that have been previously proposed, I think they should be corrected to lower values, as a planet that has stored or that can store a lot of water in its interior will simply have a smaller cross-section. And so the evaporative loss must be less efficient. Exactly. So this is one implication. And another implication is, for example, if you have the same effect for sub-Neptunes, that sub-Neptune magma oceans can actually store large amounts of water, then we would expect to see subsolar or substellar water abundances in their atmospheres, something that is discussed for giant planets, but I think we maybe don't yet have a large enough sample for sub-Neptunes. Yeah, anyway, so I think this is the conclusion for this second part, and I will take questions at this point.
Thanks, Caroline.
Thank you.
Wonderful talk. And I'll take up questions right now. If you have questions, you can type in the Q&A box and you can raise your hand. I can unmute you if you have questions. So there's a question by Robert. It says, how does error from changing the assumed core mass fraction compare to the differences between the three types of interior models in your radius mass plots?
I don't understand the question. How does error?
How does error from changing the assumed core mass fraction compare to the differences between the three types of interior models in the radius mass plot?
So I guess how different are core mass fraction estimates on mass radius plots? I don't have plots that compares this actually. I think I have the feeling these are two also, I mean, they're a bit different. Let's say I think there is a diversity in rock composition. So this is something that we should be aware of. And I think the trend, let's say, that we see plotting stellar abundances versus planetary densities shows that there must be some link between the compositions, between the refractory compositions of a star and its planet. And the addition of water is another component in this. And here in this study, actually, the last part where I discussed water-rich magma oceans, I haven't shown you any results that depend on the rock composition. And yeah, that's also future work. There is a dependence of how much water you can store on the actual rock composition. So I guess at the moment it's also hard to distinguish these effects simply as data is degenerate. But the more insights we have, maybe eventually we can, with atmospheric characterizations, we could disentangle these cases better.
And then Liang had a question. So he said, thanks, a wonderful talk. May I ask if you have some experimental data showing that water decreases melt density significantly at extreme pressures of the super Earth, pressures that are greater than 100 GPa. It continues at high pressures that are greater than 100 GPa. Several theoretical calculations show that hydrous and anhydrous melts at the same density. This is because the density of water in magmas, that is water molar mass derived by its molar volume, is similar to that of other components such as MgO at high pressure.
Yeah, very good point. So I am using Beigain. I don't know how to pronounce the name. And they're suggesting that there is a constant decrease in magma density by for each added water mass fraction of water, and this is nearly constant and rather independent of pressure and temperature, especially actually for these higher pressures. I wonder what the link leads to, but I will test this link later.
Hey, Burkhard, can you please go ahead and ask your question?
Yeah, thank you, Caroline, for this nice talk. I assume all your models, they assume underlying equations of state. So could you just tell us a little where you took them from, who you cite, and how do you study mixtures? That would be good to know for the people who work in that field and derive some of this result. Thank you.
I would have to cite many studies now. The best thing is to look in our recent paper, Dorn and Lichtenberg. There I'm listing all the equations of states. So it's a relative large collection for the solids as well as the liquids for different compositions. I saw Sarah Stewart is also in the audience. So for example, I'm using also her equation of states for molten Mg2 as IO4. I think the best would be the reference. I hope that's a fine answer for you.
Okay, thank you. I would just say you should probably give some credit to people who work in that field when you give these talks, because your results to some degree depend on it. That's just my comment. Thank you.
That's true. That's a good point. Yes, I will do that. I often think, so it depends a bit when I speak to observers, I have the feeling it's not that interesting, that these are rather technical details. So, but it's a good point that you're raising. Thank you.
Hey, Maxim, go ahead and ask the question.
Thank you for the great talk, Caroline. I was wondering what would be the importance of the equilibrium temperature of the planets. Correct me if I'm wrong, but I think in your model, in your atmosphere model, you assume that the you assume an isothermal stratosphere, which is at 400 K, so that you never have condensation of water. And I was wondering whether having condensation in the higher atmosphere might affect the results. If that's something you had been thinking about.
So we are here. We are looking at relatively hot cases. So it's true. We are using an equilibrium temperature of 400 Kelvin. We assume that down to the tropopause, we have an isothermal profile, and then we follow the water adiabat in the steam atmosphere. Doing this procedure or parameterizing the steam atmosphere like this actually matches well with results from Martin Tourbet. Sorry, I wanted to say something. You raised another point, I guess. Was there another?
Yeah, I was wondering about the possibility of having condensation, because I guess
condensation,
that's
yes, exactly.
Also, right?
So by construction, these models, like when we follow the adiabats of water, like after the tropopause, we actually never allow water to condense. So by construction, this is not possible in our models.
All right.
But one could go to conditions where this would occur.
Mm-hmm. Yeah, maybe that's the next question that doesn't matter at all, but I was wondering if you had like massive condensation, if that could affect the density of the atmosphere to such an extent that it would have an impact on the transit radius, but maybe.
Yes, I mean, if you have condensed water, I think that's the work from Tourbet et al., where he looks also at the range of the TRAPPIST planets. Yeah, there is a huge difference whether you have condensed water or gaseous water on the final total radius.
So here, when you say condensed water, here do you mean an ocean, or because I'm thinking about clouds, for instance, like not necessarily
here. Here I think of an ocean in that case, but I mean, as I want to investigate these hot worlds, I don't go down to conditions where I have
yeah, I was just wondering whether you might have clouds high in the atmosphere while still having a molten silicate surface. But maybe I really don't know. Maybe it's not that relevant.
I mean, here we don't have a background gas in these models. I simply assume pure water. So in that case, there cannot be clouds, I guess, if there's just water. You need a medium to condense it in, right?
Well, I guess if you reach the, yeah, well, I guess.
I mean, otherwise you condense, yeah, you simply rain out your water and form a water ocean.
Yeah, well, maybe that was a naive question.
But it's a good question. Yeah, thank you.
Thanks for the answer.
Raj, go ahead and ask the question.
Hi, Caroline. Thanks for the talk. Great. I was wondering, and again, I haven't read your latest paper yet, so maybe the answer is there. Am I assuming correctly that in your model of magma ocean, you are assuming the magma ocean to be like a complete magma ocean, meaning there is no base to it, or the base is all the way to the core mantle boundaries for these bodies?
This always depends on the pressure, temperature, structure. So depending, that's why I said for larger planets, normally if I have the same boundary conditions for planets of different masses, then the larger mass planets, their extent of magma oceans are smaller just because they have a steeper pressure gradient. And so I'm I mean, I assume these interiors to be fully adiabatic. That's an assumption that I'm doing. But then I compare my temperatures in the interior to the melting temperature, and to see whether I'm in the molten or solid phase.
Yeah, I guess where I was going with it is, do your models incorporate sort of water storage and partitioning between the solid silicates and solid silicates and the molten silicates as well, or is it just is it just an ingassing into a molten layer, and you are just assuming the solids to be completely devoid of solid silicates to be devoid of water, or did you take that?
Yes, I'm assuming that all the solid rocks are dry, and the reason is there is a study by Oliver Shah from 2020, I guess, where he shows the effects of water in solid rocks, and the effect of it is very small. And he looks at very extreme cases where he tries to maximize the amount of water that can be stored in solid rock, but the effect on the total radius is very small, and so I have neglected this part. Yeah.
Okay, thanks. Sarah, you're up next.
Hi, Carolyn.
Hi.
That was really nice. I'm trying to think about how to test these things, so I'm going to ask an observational question because I really don't know the answer. If the bodies were layered nicely with a very compressible water on the outside versus a mixed magma water, the tidal deformation of the bodies would be quite different. And so I'm wondering for these close-in planets, if it's possible for the observers to infer anything about the oblateness or shape of the bodies. Because if you could, let's say you just do this, take your models and run them and predict how oblate they could be, or if they're tidally locked, how deformed they could be with these different interior models. And it would be interesting to know if that's something we can push observations to. Maybe somebody already knows.
That's a very interesting thought. I haven't thought about the details and whether there is actually a large difference between a magma ocean and a wet magma ocean.
Or the magma ocean plus thick atmosphere versus dissolved water. Right?
I see. Yeah.
But just wet versus dry, you couldn't tell. But just this degeneracy over thick atmospheres versus dissolved volatiles.
Yeah. My first thought was that, like, spectroscopic observations of atmospheres should tell us more about these deeper interiors, because some species, like, let's say now I've only looked at water, but there are also other volatiles, carbon species, that have also the ability to be stored in these magma oceans. And different volatiles have different abilities to dissolve in the magma ocean. And I would guess that we could see within the population some trends that's, I don't know, some C2O ratios are lower than expected for some planets. As carbon species, they dissolve more easily into magma oceans. I was thinking along these lines that this could be a possible observational handle that we could have on these models, because but the tidal deformations is also an interesting aspect. Here the largest effects are for the very small planets, or the rather smaller planets, and I guess that's observationally very hard if you want to see the tidal deformations. But it's, thank you for this comment.
Okay, so there's a question by Maitri. Thanks for the great talk, Caroline. Can you consider partial melting and formation of magma pools in your models? What differences would you expect if that were the case in Earth-like planets?
Magma pools? Can you say this
maybe-
again?
I think
Yeah, magma pools.
magma pools. So maybe like small magma ponds or something along those lines.
I don't see how, like, I think what drives the study is that we can measure these effects on these different interiors given the given measurements of planet radii. And if you don't have a global magma ocean, but only a local magma pool, I think the effect is very tiny. Like the amount of water that could be stored in a magma pool should be, I guess it's not, you can't sense this with a measured radii. So, but yes, I will consider partial melting if that were the case. And the question is, what difference would you expect if that were the case in Earth-like planets? I think I don't understand the question. I'm not sure what's in which sense Earth-like. Yeah, if the person is here, maybe the person could explain more, but I guess, yeah, magma pools is it's simply the volume of these pools are much smaller than global magma oceans.
And there's a question by an anonymous attendee. I'm a little confused about the temporal factor. The planetary surface should cool quickly to reach thermal equilibrium with stellar irradiance. So surface magma ocean should be rare at any given moment. I'm missing something in your statement that magma oceans are common.
Maybe I should simply go back. To the slides, or this one in here. So all, like, those planets that have conditions that are temperate are really these exceptions. Otherwise, all these red colored planets, they are within the greenhouse limit. So when you have any type of atmosphere on top, then you have such an increase in temperature such that the surface temperature of your planets is hot enough that you can have a magma ocean underneath. And yeah, the temperatures, I'm sorry, this, I should, yeah. Do you see that this is a 2000? It's not a 200. So in here, it's actually 2000. Maybe this is what is confusing. So these planets in yellow have temperatures above equilibrium temperatures above 1700 Kelvin, and rocks must be molten even if there's no atmosphere on top.
Maxim, do you have another question?
Yeah, actually, that's I have a sort of a partial answer, I guess, to Sarah's question, and that's that one of my colleagues at my previous institution in DLR in Berlin writes his thesis on the possibility to infer the K2 of I think that was for hot Jupiters, based on the light curves of transits. And I think in the case of hot Jupiter, that might possibly be doable, although that would require, I guess, multiple observation. I'm not by no means an observer, so I don't really know. But there has been some work done on this field, and I can also provide the references if you want.
Okay. So I have a question, Caroline. Do you consider what are the redox conditions that you consider in your models when you calculate this partitioning solubility of water in the silicate melts, like of all these? Do we have any constraints on the oxygen fugacities?
I mean, here I actually simply started out with well, what I call an Earth-like interior, where I have like 30% of the, or 33% of the mass in the core in iron, and a mantle. I'm thinking if there is iron included. I don't think there is. I think there is no iron in the mantle for this second study that I'm showing. Exactly, I think I just used magnesium and silicon in solar abundance. So yeah.
So like, so solubility of water is like redox, like FO2 dependent, right? So in the magma ocean, so do you have an estimate of the numbers? Like, is the oxygen fugacity is like relative to the IW buffer or something along those lines?
There is an interesting paper from Bauer et al. From this year, where he shows dependence on the solubility of water depending on the rock composition. And in this case, I haven't actually included this because I was not showing different rock compositions. So, in Bauer et al. I mean, yeah, you see different trends depending on the composition. Yeah, I guess, yeah, I think that's, for me, it's future work to implement this and to test the details of it on the total radius. It's a secondary effect. That's why I haven't talked about this. Yeah.
If I can quickly jump in, there has been also several papers that have shown that the redox state of the magma ocean might be dependent on its depth, and in particular in the case of super Earth, where you might have potentially a very deep magma ocean, there would, it seems, be more prone to be oxidized and thus to go in the direction of having water.
That's the G. Deng paper.
Yes, exactly, and the one by Armstrong.
Yeah.
2009.
Yeah, exactly. Yeah. Very true.
Thank you. Are there other questions that from the audience? Okay. Yeah. Thanks again, Caroline, for the amazing talk, and thanks for taking the time out late at night in Zurich.
Thank you.